All right, are you ready to kind of get amped up a little bit today? Because we're going to dive deep into the world of electric currents,
I'm ready.
but like not just the basics. We're talking about going a little bit further and figuring out really the effects of these electric currents and how they impact
The things that we see every day.
the things that we see every single day,
Yeah,
things that we use every day, and honestly kind of take for granted.
absolutely.
And I know that I do so.
Yeah, we don't think twice about flipping a switch or plugging something in.
Exact.
But there's so much happening behind the scenes.
There is.
It's fascinating.
It's pretty amazing. So I guess to kind of kick things off,
Yeah.
have you ever noticed those like symbols
Oh, yeah.
when you look at, anything related to electrical currents or circuits?
Like a wiring diagram or something like that.
Exactly.
Yeah,
They
absolutely.
look almost like hieroglyphics.
They do. They're like a secret code,
They are.
but they're actually really important.
Well, they have to be right because they're all over the place.
Right. They're called electric symbols, and they're like a universal language for anyone working with circuits.
So it's like a shared language for electricians.
Exactly. It makes it much easier to design and communicate about complex electrical systems.
Okay, so kind of like engineers have their own language and architects have their own language.
Precisely.
Electricians have their own language, and this is it.
Exactly. It's a shorthand way to represent all the different components.
So you don't have to write out the whole word. You could just use the symbol.
Exactly. It's like a visual shortcut.
Got it.
For example, a straight line represents a wire.
That was pretty simple, right?
That one's pretty straightforward.
But what about something like a battery?
Oh, yeah, that one's a little more interesting.
I would think it looks like a stack of little boxes.
It does, doesn't it?
Why is it called a battery when it seems like it's made up of multiple cells?
That's a great observation. You've hit on a key distinction.
Uh-oh.
So a single unit that generates electricity,
Okay.
that's called a cell.
All right, so that's one little box.
Exactly. Like a AA battery is a single cell.
Okay.
But a battery is formed when you connect multiple cells together.
To make it more powerful.
Exactly, to boost the overall power output.
So if you have like a big flashlight that takes like 6D batteries,
Right.
that's actually a battery?
That's a battery. It's a combination of multiple cells.
That makes so much sense.
Yeah, and they're typically connected in a series.
Okay.
Positive terminal of one cell connects to the negative terminal of the next.
I've noticed that in battery compartments, there's always a little plus and a minus.
Exactly. Those signs are crucial for understanding how the current flows.
So it's not just random.
No, not at all. It's all about creating a pathway for the electrons to flow.
And the plus and minus signs are guiding the traffic.
Precisely. They're like road signs for the electricity.
This is making so much more sense now.
Good. I'm glad to hear it.
Now, I remember as a kid being so confused about those little plus and minus signs.
Well, yeah, I can add.
I never understood what they meant.
Well, it's not always obvious until you start learning about circuits.
Yeah, but now it's like, oh, that's how the electricity knows where to go.
Exactly. It's all about creating a closed circuit.
Okay, wait, so before we even get to a closed circuit,
Yeah.
what is a circuit?
So a circuit is essentially a pathway that electricity can flow through.
Like a little racetrack for electrons.
Exactly. And for the electricity to flow, that pathway needs to be complete.
Okay, so that's where the closed circuit comes in.
Exactly. In a closed circuit, the pathway is complete, so the electrons can flow unimpeded from the power source through the wires to the device and back to the source, creating a continuous loop.
So it's like a closed loop.
Exactly.
Okay, I think I'm getting that.
Good. It's a fundamental concept.
But what happens if there's like a break in that loop?
That's when we have an open circuit.
Roadblock.
Exactly. If there's a gap in the pathway, like a broken wire or a switch turned off, the flow of electrons is interrupted.
So flipping a light switch is essentially like opening and closing a circuit.
That's a great way to think about it. When the switch is on, you're closing the circuit and allowing the electricity to flow to the bulb.
So that's why the light turns on.
Exactly. And when you flip the switch off, you're opening the circuit and stopping the flow of electricity.
Okay, so open circuit, no flow, closed circuit flow.
You got it.
This is starting to make so much more sense.
I'm glad to hear it. It's all about understanding the flow of electricity.
Okay, so we've talked about circuits and the flow of electrons, but what about the heat?
Oh, yeah, that's a fun one.
Right, because electricity can generate heat, and that always kind of blows my mind a little bit.
That's pretty amazing, isn't it?
How does that even work?
Well, it all boils down to resistance.
Okay, resistance, we've talked about that a little bit.
Right. Resistance is the opposition to the flow of current.
So it's like friction.
Exactly.
Yeah.
As electrons flow through a wire, they bump into the atoms in the wire's material.
Okay.
And these collisions create friction, and friction generates heat.
So it's like those tiny electrons are bouncing around on the wire and creating heat.
Precisely. It's like a microscopic dance party.
Okay, so the more resistance, the more heat.
Generally speaking, yes.
And different materials have different levels of resistance.
Exactly. Some materials like copper are good conductors.
Right.
They have low resistance, so they don't heat up as much.
That's why we use copper for electrical wiring.
Exactly. It's a safe and efficient conductor.
Okay, but then what about those wires that are designed to heat up?
Ah, you're talking about heating elements.
Yeah, like the ones in a toaster or hair dryer.
Precisely. Those are made from materials with high resistance.
So when current flows through them, they get really hot.
Exactly. That's how they generate enough heat to toast your bread or dry your hair.
It's so cool how we can manipulate this heating effect to create so many useful devices.
It really is. It's all about understanding the properties of different materials and how they interact with electricity.
All right, so before we move on to the next mind-blowing concept, do you have any questions about electric symbols, circuits, or the heating effect of current?
I don't think so. I think we're ready to move on to the next fascinating aspect of electricity.
Okay, great, because this is where things start to get really interesting.
I can't wait. So it seems like we've got a good handle on, those basic building blocks.
Yeah, like those symbols, the circuits, the heating element.
Yeah, and how they all work together.
Right, exactly. But now I think it's time to get to the heart of the matter.
Okay. I like where this is going.
What is electric current?
Ah, yes, the million-dollar question.
Because we've been talking about, circuits and the flow of electrons, but we haven't really defined what electric current is.
Right. We've talked about the river, but not the water itself.
Okay, I like that analogy.
So in the simplest terms, electric current is the flow of electric charge.
Okay, so it's not just some invisible force.
Nope. It's the movement of tiny particles called electrons.
So those electrons are the actual electricity.
Exactly. They carry a negative charge, and their movement is what we call electric current.
Okay, so I'm picturing like a stream of electrons flowing through a wire.
That's a great way to visualize it. Imagine millions of tiny electrons all moving in the same direction.
Like a tiny little electron highway.
Exactly. And just like a river, electric current has a certain rate of flow.
Okay, so how do we measure that?
We measure it in amperes, or amps for short.
Ah, amps. I see that all the time.
Yeah, it's a common unit of measurement for electric current.
So like on my phone charger, it says it's like 2 amps.
Right. That means that charger can deliver a current of up to 2 amperes.
Okay, so the higher the amps, the more electricity is flowing.
Exactly. Higher amperage means a greater number of electrons are flowing through the circuit per second.
So more amps, more electrons, more power.
You got it. It's like a wider river carrying more water.
Okay, that makes sense.
Uh.
But what makes those electrons start flowing in the first place?
Ah, that's where voltage comes in.
Okay, voltage. Tell me more.
Voltage is essentially the electrical pressure that pushes those electrons through the circuit.
So it's like the force that gets the electricity moving.
Exactly. It's the driving force behind the electric current.
And we measure voltage in volts, right?
You got it. Volts are the unit of measurement for electrical potential difference, which is what voltage is.
Okay, so if amps are like the amount of water flowing in the river,
Yeah.
voltage is like the steepness of the river.
I like that analogy. The steeper the river, the faster the water flows.
And the higher the voltage, the stronger the electrical push.
Exactly. Leading to a higher current flow.
So more volts, more amps, more power.
Precisely. It's all connected.
This is starting to feel like a puzzle where each piece fits together.
It is. It's all about understanding the relationship between these different concepts.
So we've got the current, the flow of electrons, the voltage pushing them along.
Yeah.
What else is there?
Well, there's one more crucial piece to this puzzle, and that's resistance.
Resistance.
Yeah, we talked about it before when we were discussing the heating effect.
Right, because resistance is what makes wires heat up.
Exactly. But it also plays a critical role in how circuits behave in general.
Okay, so how does resistance fit into this whole voltage and current thing?
We'll think of resistance as the friction that opposes the flow of electric current.
So it's like the rocks and obstacles in our river analogy.
Precisely. They slow down the flow of water.
And in an electrical circuit, resistance slows down the flow of electrons.
Exactly. The higher the resistance, the more difficult it is for the electrons to flow.
So if you have a high voltage, but also high resistance,
Yeah.
the overall current will be lower.
Exactly. It's a balancing act between the force pushing the current and the resistance holding it back.
So it's like trying to push a heavy object up a hill.
I like that analogy. You need a lot of force to move it, but the incline of the hill makes it harder.
So resistance is kind of like the electrical equivalent of friction.
Precisely. And just like friction, resistance can be useful or it can be a hindrance.
Okay. I'm starting to see how all of these pieces fit together.
Good. And all of these concepts are beautifully intertwined in what's known as Ohm's law.
Ohm's law.
Yeah.
Okay, now we're getting serious.
It's a fundamental law of physics that describes the relationship between voltage, current, and resistance.
So it's like the mathematical equation that governs the flow of electricity.
Exactly. It's a cornerstone of electrical engineering.
Okay, so can you break down Ohm's law for us non-physicists?
Of course. In simple terms, Ohm's law states that the current flowing through a conductor is directly proportional to the voltage applied across it and inversely proportional to the resistance of the conductor.
Okay, hold on. Let me try to wrap my head around that.
Take your time.
So more voltage means more current. That makes sense.
Right.
But more resistance means less current.
Exactly. You got it.
So if you have high voltage pushing the current, but you also have high resistance pushing back,
Yeah.
the result is a lower overall current flow.
Precisely. It's like a tug of war between voltage and resistance.
Okay, I think I'm starting to understand.
Good. It's not as complicated as it sounds once you break it down.
So Ohm's law is like the rule book for how electricity behaves in circuits.
Exactly. It's a powerful tool for understanding and predicting how circuits will work.
Wow. I'm starting to see how even these seemingly simple concepts are the foundation of our entire electrical world.
They are. And understanding these principles is key to unlocking the secrets of electricity.
Okay, before we dive any deeper,
Yeah.
do you have any questions about electric, current, voltage, or resistance? So you've been talking about all these concepts, like voltage and current and resistance and Ohm's law.
Right. Those fundamental building blocks.
But how does all of this actually work in practice?
Yeah. How do these principles come to life in the things we use every day?
Like when I flip a switch and the light turns on.
Exactly. Or when you plug in your phone to charge.
Or even like bigger things, like how does electricity get to our homes?
That's a great question. It's one thing to understand the theory, but it's another to see how it all plays out in the real world.
Right, because it's not like we can see those tiny electrons zipping around.
No, we can't see them, but we can see the effects of their movement.
So how do these invisible forces power the devices we use all the time?
Well, let's start with something simple, like an electric heater.
Okay, I like heaters, they keep me warm.
Me too. So inside an electric heater, you have a circuit.
A circuit. Okay.
And that circuit is designed to convert electrical energy into heat.
Using a heating element.
Exactly. That's the key component.
The one that gets red hot when you turn the heater on?
Precisely. And the amount of heat it generates depends on a couple of things.
What are they?
First, the resistance of the heating element.
Okay, so higher resistance means more heat.
Generally speaking, yes.
And second.
The amount of current flowing through it.
Okay, so more current, more heat.
Exactly. And of course, the circuit also includes some safety features.
Like what?
Well, a thermostat, for example.
A thermostat.
Yeah, to regulate the temperature and prevent overheating.
So it doesn't just keep getting hotter and hotter.
Exactly. That could be dangerous.
Right, so even in something as simple as a heater, there's a lot going on behind the scenes.
Absolutely. It's a carefully designed system that uses those basic principles of electricity to generate heat safely and efficiently.
Okay, so that's one example. But how about like a bigger system? Like how does electricity get to our homes?
That's a great question. And it involves a much more complex system.
Right, because it's not like there's a giant wire running from the power plant to my house.
No, it's much more intricate than that.
So how does it work?
Well, it all starts with generators.
Generators?
Yeah, those are the powerhouses that generate the electricity.
Okay, so where are these generators?
They're located in power plants.
Oh, right, power plants.
And they convert mechanical energy into electrical energy.
Okay, so what does that mean?
Imagine a massive turbine spinning really fast.
Okay, I'm picturing it.
And that turbine could be driven by steam water or even wind.
So that's the mechanical energy.
Exactly. And as the turbine spins, it generates electricity.
Okay, so the generator is like the source of the electricity.
Exactly. It's like the starting point of our electrical journey.
So how does that electricity get to my house?
Well, it travels through a vast network of power lines.
Those giant towers I see all over the place.
Exactly. Those power lines carry the electricity over long distances.
Okay, but those power lines are really high up in the air.
They are. And there's a reason for that.
Why is that?
Well, it's more efficient to transmit electricity at high voltages.
High voltages, okay.
Yeah, it minimizes energy loss during transmission.
So it's like sending the electricity at a higher pressure.
That's a good way to think about it. And to get the voltage that high, we use transformers.
Transformers.
Yeah, they're like electrical gear shifters.
Okay, what do?
They either step up or step down the voltage of the electric current.
So they can make the voltage higher or lower?
Exactly, depending on what's needed.
And why do we need to change the voltage?
Well, for transmission, we want the voltage to be really high.
Right, to minimize energy loss.
Exactly. But before the electricity reaches our homes, we need to lower the voltage again.
Because otherwise it would be dangerous.
Exactly. Too much voltage could fry our appliances.
So we have transformers that step down the voltage.
Precisely. And those are usually located closer to our neighborhoods.
Okay, so it's like a carefully planned journey for the electricity.
It is. From the generator to our homes, the voltage is adjusted along the way to ensure safe and efficient delivery.
And throughout this whole process, safety is paramount, right?
Absolutely. Safety is always the top priority.
Because electricity can be dangerous if it's not handled properly.
Right. That's why we have all sorts of safety features built into the system.
Like what?
Well, circuit breakers and fuses, for example.
Oh, right. Those things that trip when you plug in too many appliances.
Exactly. They're designed to protect us from overloads and short circuits.
Okay, so how do they work?
Well, basically, they interrupt the flow of electricity if it gets too high.
So they're like safety valves.
That's a good way to think about it. They prevent damage to our appliances and wiring, and they also help to prevent fires.
So they're really important.
They are. They're like the unsung heroes of the electrical world.
Always working behind the scenes to keep us safe.
Exactly. And they're a crucial part of what makes our electrical system so reliable.
Well, this has been a truly electrifying deep dive.
I agree. We've covered a lot of ground.
We started with those tiny electrons and ended up talking about giant power grids.
It's amazing how all of these concepts are connected.
It is. And it just goes to show that even the most complex systems are built upon those fundamental principles of electricity.
Exactly. And understanding those principles is what allows us to harness the power of electricity safely and effectively.
Well said. So as we wrap up, I want to encourage everyone to keep exploring and keep learning.
I agree. Curiosity is key.
Because the world of electricity is full of wonders just waiting to be discovered.
Absolutely. And who knows what amazing new technologies we'll invent in the future as we continue to unlock the secrets of electricity.
Well, thanks for joining us on this electrifying journey into the world of electric current.
It's been a great pleasure.
And until next time, keep those sparks flying.
Stay curious.